Okay, so here's number 29, which I know will confuse a lot of people. But I thought it was pretty easy if you just label out all your things. You have 39.1 moles of helium and has a volume of 876 liters and 0 degrees Celsius and 1 atm. Temperature of the balloon is increased, so separate them. And this is 38 degrees Celsius and 998 liters. Pressure is constant, so you could just say 1 atm. And then now it's asking you for QE, QW, and delta E. Okay, that's simple enough. So delta E is equal to Q plus W. So you can't really solve for delta E yet. So you have to solve for Q and W individually. W equals negative P delta V, and Q, which is heat, equals MC delta T. Yeah, you should remember this. You should remember this from Chem last year. So you solve for Q. You have the moles, 39 point. God, that's annoying. Q equals 39.1 moles times 20.8, and this is the this is C, and it's given here. MC delta T, the specific heat, the heat capacity is right here, and heat capacity is C if you didn't know. J over degrees Celsius times mole. And you also multiply by delta T, and delta T was, what was delta T? 0 to 38, so I don't know why I flipped the page when the problem's right here. Okay, 38, and this, you multiply this out, this becomes 309, no, 30,904.6 joules. And that becomes the 30.9 kilojoules. Now you have Q, now you solve for W. W equals negative P delta V, as shown before. Yeah. That P is just, it was 1 because it's constant, negative 1. And delta V was, you just subtract these. 998 minus 876. And this becomes 122 liters per ATM. And of course, it's negative. Now, in order to solve for delta E, you're gonna need to have them in the same units. So this has, both of them have to be in kilojoules. So in order to convert this into kilojoules, all you need to do is just use that conversion back from number 25, I think. Yeah. So negative 122 liters per ATM times 101.3 joules liters per, this is of course 1 liters per ATM. Cancel out the units and you end up with negative 12359 joules, which becomes negative 12.4 kilojoules. Now now that you have both of them, delta E equals Q plus W. You have W and Q, so 30.9 kilojoules, 30.9 and negative 12.4 minus 12.4, 18.5, I think, if my mental math is wrong. My bad. Delta E. How long is this? Okay, I guess I could just do number 31. Number 31, why are high temperatures needed to convert N2 and O2 to NO? Yeah, this is not even a math problem. 31. This is just, it's just logic. High temperatures. It just means that high temperatures are needed for reactions to occur because of energy transfer, and it's gonna be an endothermic reaction because it's accepting energy. N2 and O2, they have to absorb energy from the high temperature environment for this to occur. Yeah. That is number 31 in a nutshell. Number 33. A. When solid KBr is dissolved in water, solution gets colder. Okay. If it's getting colder, it's obviously endothermic. B. Burned in a furnace, exothermic. C. Solution gets very hot, exothermic. D. Boiled in a tea kettle, that is endothermic. If you don't know how to do this, it's just endothermics are when it absorbs energy, when it takes in energy, and exothermic is when it releases energy. And usually it's in heat. Energy is in the heat because we're dealing with thermodynamics and thermochemistry. So you notice how water is just absorbs that heat energy from the tea kettle thing, and this If it's getting hotter, it's obviously releasing energy. If it's burned, it's obviously also releasing. And when it gets colder, it's absorbing. Or, yeah. Yeah, it's just absorbing. There's no way it could be exothermic.